Okay, so I can close the assembler stuff so I don't pre-scare people who are going to take assembly next semester.
Wasn't this class completely full at the beginning of the semester?
Well, I think we're getting slightly better attendance now. All right, so let's go ahead and get started. The solution of the homework assignment is now going to be disclosed. So I did create a second assignment for people who want to turn it in again or turn it in late. Okay, so this is the second one. So it's now time to disclose the answer, which I think is here, but I could be wrong. Yep, that's the one. Is that the one that you guys had to work on?
Yeah.
Yep, okay. So let me zoom in and then we can take a look. Maybe one more level. There we go. Okay. So I have to write out the distribution law because I keep forgetting those two so I have to write it out first. So the first thing is to get rid of the implication. So the implication is now turned into the negation of the first part or the second part. Or is that the original? That's the original statement, I think. Yeah, that's the original statement. So in the next one, I got rid of the implication by expanding the implication into the negation of the first part or the second part on one side. And then on the other side, it is De Morgan's law. So I applied De Morgan's law so that this negation gets distributed into the inside. But then I have to change the conjunction, which is implicit between the Q and the open paren, into the conjunction turns into a disjunction. The and turns into or. But then the negation is distributed into the components so that we have the negation of Q, and then on the other one we have the negation of S or not T. So is that okay? From the first line to the second line? From the second line to the third line, it is De Morgan's law, and then De Morgan's law, and then the associative rule. So from the second line here, I apply De Morgan's law. So De Morgan's law is looking at P or Q as an entire thing. Okay, so I'm not breaking it apart yet. So it becomes the negation of the negation of this. Double negation cancels out, so we only get P or Q left. The disjunction turns into a conjunction, and then R is negated because of the distribution of the negation from the outside. So the first term becomes P or Q, and then the whole thing and not R. On the other side, I also applied the Morgan's law to the inside. So the negation of S or not T becomes not S and not T, which I simplified to just a single T. Okay. And because this is a or, this is a or, that is just an or, so I just took out the parentheses because of the associative law. There's no need to use parentheses. Is that okay? All right. So from that line, which is the third one, to the fourth line, I use distribution. So the distribution only applies to this term. So I took P and not R outside, and then do an OR with Q or not R. So that becomes this term. Nothing is done to the other side. Yep.
What if you treat P or Q as one thing and then distribute it over before going and distributing it fully to not R? Like, say for instance you substitute it with another version of it, so P or Q stays together while you distribute it.
You can do that, but that means you will have something to expand later on. You can do that. There are more than one ways to get to the answer. This is just one way, and it's not even probably the optimal way. Some of you may have a shorter proof than this. That's entirely possible. So after the distribution, I do another distribution. So this one is looking at these two and do a cross product. And then this cross product has to do with this particular distribution rule. So P and not R, or Q and not R, is now distributed, kind of like do the cross product thing. So P or Q is one term, P or not R is another term, not R or Q is one term, and then not R or not R is another term. So I spelled out every single term just to make sure that I do not miss a term. Okay. The other side is not changed. And then I look at, and then what I did was I look at this entire thing as one, okay, I look at each component of this conjunction as each individual term, and then I distribute the OR again, and this time I'm including the not Q. So that's why you see the not Q is now included into the individual terms. So we have not Q, not Q, not Q, and not Q introduced into each term. And then I did some simplification before expanding any further. So that is a really useful technique, is to try to simplify when it is obvious. It's like, oh, these terms are not doing anything, so let's get rid of those. So the terms that I got rid of is this term first, because we have Q or not Q. So the Q or not Q, which is this part here, is simplified to a 1, and then 1 or anything is just 1, so that whole thing simplifies to 1. Same thing applies to the other side. We have Q or not R. That also simplifies to just a single 1. And then this one, because we have not R or not R, that simplifies to just one single not R. So I did some simplification here, and then just to make it obvious, in the next step, I got rid of the 1s, so we only have the non-1s left in the terms. And then these two simplify again, because of these two can simplify again, because this term is more specific compared to this term. So when you have two terms in a conjunction, one term is more specific, we can get rid of the term that is more general. So we only left with the one that is more specific. And then I just do another extension using the distribution here. So I look at not Q or not R as a single term, and then I distribute it over the not S and T. So we end up with not Q or not R or not S, and not Q or not R or T. And Sean watched me do it too on Monday. Sean was really like, well, is this really supposed to be this complicated? And I told Sean, like, I don't know, I haven't tried it yet. So I went back to my side in the design hub and just sat down and go like, okay, let me work on this. But there may be another way that makes it even easier or simpler. But during the derivation, there were a few times I was questioning myself. It's like, is it really the same? So what I did was I used a spreadsheet to double check. So I can show you the spreadsheet that I used. Let's see, this is cisp440. Did anyone use a spreadsheet to double check your, okay, was it helpful? Yeah, because you get to visualize the whole thing. And if it doesn't match, it tells you where you might have made an error. So that is the useful part of it. So let me see, where did I put it? CNF, here we go. Okay, so this is the spreadsheet that I used to double check my answer. I showed you guys this technique already. I think I shared a document with this. This one is not even as good, okay, because if you look at the equation, they're not as expandable as the one that I gave you guys on Monday. So we have n here. N goes from 0 to 31 because we have 5 variables. So I have to work with 2 to the power of 5, that many big patterns. So because the first one is 0, the last one is 31, the rain is pretty loud.
Yeah, it's quite soothing, I'm sorry.
Huh?
I said the rain is too soothing.
Soothing one side. Okay?
Yeah, I'm gonna sleep.
Now there's some way that I read about a technology to stop rain by shooting a sonic blast into air, so that you basically disperse the rain.
Yeah, they have that on Metal Gear Solid.
What?
They have that in Metal Gear Solid 5. You can actually unlock that in a mission. So if you're doing a mission that's raining, you just call the strike team and you get rid of rain.
But it's not just a game technology. I read an article somewhere that
Oh, really?
yeah, it is actually real.
Man.
Yeah. So when you look at these, this particular cell, I know we are not used to reading Boolean expressions using a prefix format, but that's what it looks like when it's in prefix format. Okay. All right. So this is the Boolean expression in prefix format, and it is representing the original expression. This one is expressing the one that I have done all the conversion. So I have to make sure that for every single row, the original expression comes up with the same value as the one that I have derived in CNF. So in this particular case, I did get exactly the same result in every single case. So that kind of proves that my CNF does contain the same logic as the original expression. Are there any questions about the answer to this question? Any questions? So after Monday, I'm assuming most people got it. Yep.
When you were writing down the steps on the side, like when you put notes, you were distributing, using
Yeah.
Morgan's, were we supposed to do that for the homework?
No, you're not. You don't need to do that. But if you skip a few steps where I cannot make a connection, then you get points deducted.
Okay, and
If it's obvious, like the ones that I did are what I would consider obvious.
yeah,
Like double negation, you don't have to explain. Oh, we're getting rid of double negation, or the one. You don't have to say, oh, the one is redundant, or it doesn't have to be in a conjunction. So those, you can just kind of, you can skip a few steps if it makes sense. But the Morgan's laws are important.
and the second part is
Yep.
for like let's say our next exam, should we be expecting like a CNF?
Yes. So you will have a similar question, but it will be simpler. So
Okay.
so I'm going to test that one and make sure that we can do it in just a few steps and not that many steps.
Okay.
Yep. All right. So with this out of the way, it is time to unlock the next question. So let me see, where is it? Right here. Okay. So I got it set up already. It's just that because we have not talked about the solution, I cannot unlock the homework assignment. So now we can actually unlock it. So let me click it and change the due date first, because I was originally intending to release this one on Monday, but since we extended the due date, or we allowed late submission on the previous assignment, so now this one is going to be extended. So it'll be next Wednesday. It's due on next Wednesday.
Well, yeah.
Wow.
No, man, it's raining soon, man. I'm trying to fall asleep and shit.
Alright, so this one is now saved and published. So let me read the question first, just in case you guys have any questions about this, I can answer those. You can see how this particular new homework assignment is starting with the solution of the previous one. Okay, so I start with the CNF from the previous homework assignment, and now what we need to do is to prove or disprove two potential theorems. The first theorem is T implies S and R. Okay, that's the theorem. So you have to tell me using the technique of resolution. You have to tell me whether this is true or not. But you have to use resolution and prove by contradiction. So the same kind of stuff that we talked about in class. So that's the first one, and you have to do it step by step. Okay, so every single step you have to show me which two expressions are resolving to which resulting expression. And then the second theorem that I want you to either prove or disprove is the one below, which is Q and R implies T. So those are the only two theorems that you have you have to prove or disprove. But the trick is you have to use resolution proof by contradiction, and your CNF. And you can see that neither of these is the CNF. Doesn't matter because you don't want to convert this into CNF. You have to convert the negation of that into CNF. I can watch people running.
I wonder how this is gonna show up on the capture.
Sorry?
I wonder how this is gonna show up on the capture. A lot of white noise.
I wasn't watching him running. It was somebody else running from a distance. Oh, I can see the highway being all slowed down and all. I mean, this is. I'm just gonna let it rain a little bit because there's no need to try to compete with the rain here. There we go. Okay, so are there any questions about what this homework assignment is about and how to go about doing it? Okay, the module is going to be important. It's going to be helpful because there are examples to show you how resolution works. Yep.
So I'm wondering, to start off, we just negate the whole thing and then we combine it.
You negate the theorem that you're trying to prove,
This,
and then you convert the negated theorem into a CNF. You connect that CNF to the CNF that is already the solution of the homework due today, and then you do the resolution. Can you use what? Implication?
to connect
No, they're all CNFs. So the result of resolution is connected to the rest using a conjunction. Yep. Wow. Oh, I see like 4 people under one umbrella. And then there are 2 people who are walking very leisurely in their rain suit. Raincoats, so they're just kind of like walking by and enjoying the rain. And there are some people running, to their destination. Cool. Wow, that is some rain. Alright, so if there are no questions about this, I'm just gonna save it. Okay, it's already published, so it's all good. And we can just go back. Alright. Alright. But when the rain is going to let up a little bit, I will start to talk about counting and events and stuff like that. Or I can turn on this thing. So it can be louder than the rain. And of course it's gonna let it up right at the same moment, right?
It's giving you a chance to put it on.
Yep. And then it's gonna.
Professor Tech, you know what you need? You need a personal Samuel Jackson translator.
I like his character in XXX,
Yes.
especially the sequel. And he was just talking about, something, and then he was killed in an explosion.
Because Samuel Jackson talks like really loud, like Dave Chappelle joke. So like you need somebody that can like just talk loud over the rain.
Yeah, but he's a lot more expressive than I am.
Look, you do it like that.
Yep. Okay, so we're going to talk about these terms in discrete probability distribution. So we'll first talk about what is a trial. A trial is a single attempt to do something, especially involving choosing something, or it can also apply to something that has just a single outcome. Okay, So in many examples, like flipping a coin, it's one single trial. Okay, you flip a coin once, that's one trial. You flip a coin again, it's a second trial. Is that okay? In the case of selecting the balls, from a lotto game, picking one single ball out of the basket is a single trial. Is that okay? So it is kind of individual. A single trial cannot be divided into any smaller steps. So each trial has a set of a set of possible outcomes, and this is what makes it discrete. Is we know the exact possible outcomes, and it is basically a set of a known size. It cannot be unlimited. Each outcome represents a possible trial result of a trial. So a trial is an action, it results in an outcome. And then each outcome is representing a possible result. So a single trial has multiple outcomes because each outcome is a possible one. So if you look into flipping a coin, okay, the trial is flipping a coin. The outcomes would be a head or a tail. Is that okay? So are we getting the terms okay so far? Okay. So the next term is an experiment. An experiment is a series of trials where subsequent trials may be affected by earlier ones.
Oh, still.
Yep.
Oh, by the way, what is this called again?
Huh?
Can
I can't hear you.
oh, I said, can you scroll up?
Counting. It's just counting.
Okay.
And of course, the moment I pick up the mic, it stops hailing, and then I put it down.
I have this embarrassing rash on my. Oh wait, you can hear me.
I don't know. I cannot do Samuel L. Jackson, but James Earl Jones is easy.
Okay.
Yeah, you just click a button and say, "I was never here." Right in The Hunt for Red October.
Yeah.
Yep. All right. An experiment is a series of trials where subsequent trials may be affected by earlier trials. An experiment has its own outcomes. So let's think about just flipping a coin twice, okay? So flipping a coin the first time is one trial. It has two possible outcomes, head or tail. Flipping the coin a second time is a second trial in the same experiment. And then it also has its own possible outcomes, which is head or tail. So when you look at the entire experiment, which consists of two flipping a coin twice, then you have four possible outcomes, because you can have head head, head tail, tail head, and then tail tail as the four possible outcomes of the entire experiment. Is that making any sense? Is that okay? All right, cool. So in general, the outcome of an experiment is represented by omega, and this omega, by the way, has nothing, absolutely nothing to do with the omega set in propositional calculus, which represents the set of all the operators. Okay, so this is just, we pick the same, Greek letter, because there are only so many letters, right?
There's also combinations of the Greek letters, and you learn how to read it.
Yep. But mathematicians do not like to type.
Oh, that's
So we
true.
choose one letter. And early programmers do not like to type either. So that's why when you look at all the C programs in earlier textbooks, all the variables only have one single letter. Either that or it's full bar, right? or combinations thereof. It's only these days when you have Campbell casing, when and a single variable, when you look at the name, is a complete sentence.
I'm gonna put my own program in.
Okay. So now that we understand the terms, we want to look at general counting. In other words, how do these things tie in with each other? So what we want to do is we look at an experiment, and we use T subscript I to represent a set of outcomes of a particular trial, and I use it I as an index. Okay? So when you want to look at the outcome of the entire experiment, it becomes the Cartesian product of the outcomes of individual trials. Now that only works in one case. Okay? That only works when the outcome of one trial does not affect the outcome of subsequent trials. Okay, flipping a coin is a good example. Okay, if you flip a coin and it lands on the head, does it mean the next one cannot land on the head, or it has to land on the head? It has no bearing whatsoever of what the next trial can, what outcome is possible from the next trial. Is that okay? But yeah, go ahead.
Well, unless you know the amount of force you're coming.
Unless it deforms the coin itself.
Well, no. When you can predict it according to the force, like how you flick it.
But the way it turns out is not going to be affected by the first one. Now you can predict it. You can collect information and start to form your opinion.
No. What I'm trying to say, you can actually make it fall every single time the same way. If you know exactly the amount of force you need to predict the exact same.
Okay. So you're saying that if you can refine the way you flip the coin and make it very, very reproducible, then it can produce the same outcome again and again. But you're not taking into consideration of air turbulence, whether the AC is on or not. Of course, there's also the quantum mechanics involved.
Okay, go over that real quick. I don't want to take some notes. Yeah, that's a good challenge.
So that works out. Okay, so we're gonna have to invite Samuel L. Jackson. I also like him in what is that movie about Richard Spies, and he's playing the villain.
The Kingsman.
The Kingsman, that's right. The first one, right? You know, he's playing the villain, where he's afraid of blood, right? So he shot the British spy and go, ew, I cannot handle this. All right, so this is good. Technology versus Mother Nature. Yep.
What's the variable m represent?
Variable m.
M, yeah.
M is the number of trials in the experiment. Is that too loud? No? Okay. Because the rain is pretty loud too.
What did he ask?
He was asking what is M representing. M is representing the number of trials in this particular experiment. So I just need to give it a number so that we know when to stop. So of course, in this case, if I use the pi symbol for a series of multiplication, then I can just do a big pi. Oh, by the way, happy Pi Day.
It's actually pronounced P, not pi. It's because it's a Greek letter. P, not pi.
But I want pi.
Okay, fine. Apple pie.
So happy P Day.
Yes.
And I think the current weather condition concurs. Happy P Day. Yeah. Okay. So when you look at the cardinality of the Cartesian product of all of the individual trials, it's really just n to the power of m, where n is the cardinality of each outcome set. But we are assuming they're the same, so that's why it is just n times n times n times n, m many times. So is that okay so far? So this is the easy one, okay? This is also called with replacement. In other words, if you flip a coin, it lands on the head, you're not removing head as a possible outcome from subsequent coin flips. So it is called with replacement. The next one is called without replacement. So this is a restriction in many cases, it is without replacement. Like in the case of picking numbers in a model, it is without replacement. Once you have drawn a particular number from the basket, that number cannot be drawn again because it is no longer in the basket. So in that case, it is without replacement. So in that case, it gets a little bit complicated. Okay, so let's go ahead and take a look at the details of this particular section. And there's a lot of symbols that is involved. So the important part is we start with a set T. So T is just the starting set in this case. And we also use the notation of n equals to the cardinality of T. So we say that for the first trial in the experiment, we start with a set T, and there are n things that you can choose from in the first trial of an entire experiment. Is that okay? That is really distracting. The rain. Well, it's a good thing that we're inside.
Oh, just like how the integrators teach outside.
I'm pretty sure there are some classes that have to be taught outside. Okay, so the next paragraph is saying, okay, what if E0, E's subscript 0, is an element of T, and that turns out to be the outcome of the first trial, or I call it trial 0 because we like to count from 0. Then this particular element, E0, is no longer available for trial 1, the next trial. Is that making any sense? So that means the outcome set of the second trial, or trial 1, is going to be T minus the set consisting of E0 as the only thing inside. Is that making any sense? It is contained one fewer element, whereas that element was the actual outcome of the first trial, or trial 0. Is that okay? So using this method, we can now say that, so using E subscript I to represent the actual outcome of trial I, then we can see that for trial I, the outcome set is going to be this. So let's take a look at this expression here. And let me zoom in just a little bit because we are just focusing on that part here. So we are focusing on this particular set. So for trial I itself, the number of possible outcome, or the possible outcome itself, is going to be whatever was originally available for trial 1, for the first trial, minus the union of all the elements that have been picked in the previous trials. Okay? It seems to make sense. It's just that there's a lot of symbols involved here because we have to use a union, and then we have the union with every single singleton set here, and then each set for each E subscript J, it is representing what was chosen or what was the outcome of the earlier trials in the same experiment. Is that okay? All right. So when you look at the cardinality, it is not a big mystery. It is really just T minus the cardinality of T minus the union of all the elements used in the earlier trials. Is really just n minus I. Is that okay? So for trial 0, we get n choices. For trial 1, we have n minus 1 choices. For trial 2, we have n minus 2 choices, and so on and so forth. That seems to make sense, right? Okay. So just for counting applications, okay, if you're not really interested in the actual elements and we just want to know how do we count this, then we can basically say at the end of the entire experiment, okay, so we are now talking about m trials in an entire experiment, and they start with n elements or n possible outcomes initially. So we're basically saying, okay, n minus I, where I goes from 0 to n minus 1, n minus I is representing the number of possible outcomes for trial I itself. But because all of those things need to be multiplied, so we use a big pi notation here to basically say, yep, we are multiplying all of these things together. So that becomes, okay, so to go from this step to this step, what did I do? I introduced a 1, right? This is just a 1 because the numerator and the denominator are exactly the same. So that doesn't sound like very productive operation here. But by doing this, I can now combine this particular pi symbol with this particular pi symbol. What is common between these two? Or what relates these two? Where we left off here, we continue here. Okay? So that's why we can combine this particular pi with this particular pi to become a bigger pi. I am getting hungry. Because we keep talking about pies. And then the only pie that is in my mind right now is apple pie.
If you call it P, maybe you won't be hungry. Oh dang, that means it can't go P.
Okay, so are we convinced that by combining this entire, operation, which is a sequence of multiplications, with this particular, sequence of multiplications, we end up with just a longer sequence of multiplication like this? Are we convinced? Yes? No? Maybe? Maybe? Okay, so we are not. Okay, so this term here is basically n times n minus 1 times n minus 2 all the way down to n minus m plus 1, right? And then this term, the first one, is picking up where we left off here. So this one, the first term is n minus m, and then n minus m plus 1, n minus m plus 2, all the way down to n minus n plus 1, which is just 1. So now we have basically n times n minus 1 times n minus 2 all the way down to 1, which is this particular multiplication. But that one has a name, we call it n factorial. Right? N factorial by definition is the sequence of multiplications of n times n minus 1 all the way down to 1. Yes?
I see that you moved the minus 1 term into the counting, but I don't know how you did from step 2 to step 3.
From step 2 to step 3. So you're talking about from here to here.
Yeah.
So I'm switching. So instead of using n minus I am directly using I itself. In other words, I look at the first number in the entire multiplication sequence, which is n minus 0, and that becomes the last one in the second series. I look at the last item, which is n minus n and then plus 1, which is just 1, and I turn that into the first of the next sequence. So I still have the same numbers throughout the sequence. The direction is different. Instead of going down, I'm now going up. But it's the same numbers. It consists of the same series. It's just going in the opposite direction. But because multiplication is commutative, I can switch the order any way I want, and that's why I can take this multiplication sequence and turn it into this multiplication sequence. Is that explaining how the trick of changing the index and also changing the expression inside?
Yeah, it's just it's hard to see it.
Oh, okay. But I did the same thing on the second one too. So the denominator had the same treatment. So with the denominator, we started off with n minus m, and then n minus m plus 1 minus 1, and then go all the way to n minus n and then plus 1. So by changing it from 1 to n1 to n minus m, and then just summing with I, it is the same sequence again, except it is in opposite order. So are we doing okay so far with how we went from the second to the third expression? So is that equality okay? Okay. The last one is really just the definition, because if you are doing multiplication from 1 to n minus m, that is n minus m factorial. If you're doing multiplication from 1 all the way to n, that is n factorial. So it is n factorial divided by n minus m factorial. So once again, n is the number of possible outcomes for the first trial, and then m is the number of trials in the experiment. This number is giving you the number of possible outcomes of the entire experiment. So are we doing okay so far with this math? We have seen something like this before, like in the previous class when we talked about the lotto.
Oh, I thought you were talking about the sigma notation.
Nope. In the previous class, we talked about the lotto game and how we generate unique tickets for a particular lotto game. So in the super lotto game, you have 47 possible numbers for the first one, and then the second number is 46, 45, and so on. Are we still doing okay so far with this? Now this is also known as, since we like the word P, now you get your P, okay? This is called permutation. That's why it starts with a P. So this is the number of permutations to choose m things out of n things. Now when we talk about permutation, ordering is important. So 1, 2, and 3 versus 3, 2, and 1 are unique permutations. They count as two permutations, not the same. Are we doing okay so far with this? So in permutations, the ordering of things inside the permutation is significant. So are we doing okay with this stuff? All right. So then we move on and talk about how in certain cases ordering of trials in an experiment is not important. So in the case of lottery, if we are choosing 1, 2, 3, 4, 5 as the lucky numbers, it's the same thing as choosing 5, 4, 3, 2, 1. In other words, the order of how you choose the lucky numbers is not important. As long as we end up with the same 5 numbers, it is considered the same. So in this case, the term is the same combination. So are we doing okay so far with the two terms? Permutation, where ordering is important, as opposed to a combination where ordering is not important. So this is also where we can relate these concepts back to something that we already understood, which is a set versus a tuple. In a set, ordering is not important. Okay, whether you list the elements of a set as 1, 2, 3, 4, 5, or 5, 4, 3, 2, 1, or any one of those different ways of including the same 5 numbers, they're all considered the same set. Okay, but when you are considering tuples, the 5 tuple 1, 2, 3, 4, 5, and the 5 tuple of 5, 4, 3, 2, 1 are considered distinct. They are two different tuples. So that's why I kind of mentioned here that a combination is kind of like a set, where a permutation is more like a tuple. So are we doing okay so far with this concept? Okay, how we are associating permutation with tuples and we are associating combinations with sets. Okay. Cool. So now the question is, if we know the number of permutations where the ordering is important, how do we get to the number of combinations? Now we figured this one out on Monday as well. Okay, remember how we first generate permutations and then we divide it by the number of permutations per combination, then we get the number of combinations. So that's why we work out the math down here. Well, okay, not quite here. This one is just saying, okay, if you have m things and you have to choose all m and the ordering is important, then by definition, the permutation of m choose m is m factorial divided by m minus m factorial. So you have m factorial divided by 0 factorial, and 0 factorial is 1. So that's why you only get m factorial back, which makes perfect sense. Yep?
Why is 0 factorial?
Because how many ways can you choose nothing? There's only one way. How many ways can you represent an empty set, basically? Or something along that line. You got nothing, so how many ways can you represent that? Just one. So the number of combination, on the other hand, is represented as either a C and an NM like this, or you could use this more convenient notation. Either one can be pronounced as N choose M. Okay, you have N things to begin with, and you're trying to choose M of those, and ordering is not important. It really is just asking how many ways can I choose M things out of N, and I just need to know what is in the final set. I don't really need to know whether I chose it first, second, third, or whatnot. Okay, so that becomes P of NM, or the number of permutations of choosing M out of N. But then you have to divide it by M factorial, because there are M ways to rearrange things. Is that making any sense? Is it intuitively making sense to you? Sort of? Okay, cool. So the math just turns out to work out to n factorial divided by m factorial times n minus m, the entire thing factorial. So we have both permutation and combination now. So this part is a little bit cumbersome, because instead of just trying to figure out the number of outcomes in the case of without replacement, I want to figure out what is exactly in the outcome set after an experiment that is without replacement. In other words, I'm not asking the question of how many unique tickets can we generate for a particular model game. I'm asking, show me all the possible unique tickets. Is that okay? So it's not a counting issue anymore. It is now becoming a generation issue. How do I generate the outcome set of an experiment where the trials are without replacement? So this turns out to be a little bit cumbersome in terms of how we can express it. So I need to use some notations here. So the notation is right here. Ti is, okay, so forget about the first two paragraphs because that's with replacement. So without replacement, then we use this notation. So omega I is representing the outcome set of an experiment involving I trials, starting with T as the initial set of possible outcomes. Is that okay? So we have several parameters. I is actually quote unquote a parameter, which is indicating which trial we are talking about. And then T as a parameter is telling us what elements, what is the set of outcomes for the very, very first trial. Is that okay? Are there any questions about the notation here? I actually misspoke. Omega I is the outcome set of an experiment that involves I trials. So that would be basically the outcome of trial 0, trial 1, trial 2, all the way up to trial I minus 1. It's the outcome set of that. Is that okay? Are we clear on the terminology itself? Maybe? Okay, so if you have questions about that in the later discussion, just let me know. I keep changing my notations, whether it's 0 oriented or 1 oriented. So omega 1, which means it is the outcome of one single trial, makes sense. Okay, so 1 makes sense, is just T itself. Is that making any sense? Yeah. So you have a big basket of balls with numbers on it. Okay, and I say, pick one number, pick one ball. How many ways can we pick a single ball out of that basket? Well, however the number that we started with. So the outcome set of an experiment that only has one single trial, it has the same outcome set as the first trial, which makes sense. Okay. So now the next question is, if I tell you what is omega 1, how do we derive omega 2? Okay, so let's look at this definition of omega 2 and see whether it makes sense or not. So omega 2 of t, okay, which means we are now talking about the outcome set of an experiment that has 2 trials, where the first trial starts with t as the possible outcomes. Is that okay? So now we have a big union, okay? And the big union says for each element E of t, okay, t, remember, is the possible outcome of the very first experiment, I want to compute this thing here. So we have E Cartesian product with t minus E. Okay, so forget about the big union first, okay? We know that E is something in t. What is that, what is that telling us? What is the meaning of this thing? So we are just looking at this portion here. E is representing the outcome of the first trial. And then the Cartesian product is how we connect a outcome of one trial with the outcome of the second trial. Okay, because the result of a Cartesian product is a set where every element is a tuple, where ordering is important. That's what we're trying to do. We're trying to figure out all the possible sequences of selecting things from the original set of t. What we are doing a Cartesian product with is t minus e, e in the set itself. So that means we're excluding e itself, but we are considering everything else in t. So, okay, that's the one way to do this is to show an example. So let me scroll this one all the way to the top, and then we'll use Notepad for an example. Okay. And I'll show the other one. Okay, so let's consider t initially to be 1, 2, and 3. Okay, simple enough. So we are now saying, okay, what is omega 2 of t? So omega 2 of t is a big union, okay, where E is in t. So that means we have 3 possible cases here. We have E being 1, E being 2, and E being 3. And then in each one, we want to do a Cartesian product of the set consisting of E only with the set that is t minus E. Okay, so what is that going to boil down to? So this is going to be boiling down to, if E is 1, then we have 1 Cartesian product with the remaining portion of t, which only has 2, 3. And then union with the next one. What if E is 2? Well, then we have 2 as the outcome of the first experiment, but then we have 1, 3 as the possible outcomes of the second experiment. And then we have another union with, what if E is 3? Well, then we have 3 as the outcome of the first experiment, and then we have 1, 2 remaining as the possible outcomes of the second experiment. Is that okay? In other words, the first line is really just repeating what I had here in symbols, but this time I'm quote-unquote spelling out the whole thing. And then the second one is expanding it, okay? I'm basically saying, okay, since we're talking about for E in t, E can be 1, 2, or 3, because those are the 3 elements in t. All right, so let's finish this operation, because this is not done yet. The first Cartesian product will give you 1, 2, and 1, 3. Is that making any sense? Because we have a singleton set 1 that consists of only 1 as an element, Cartesian product with 2, 3. So we have 1, 2 as one possible 2 tuple, and then we have 1, 3 as the second possible 2 tuple. Okay. So you can probably imagine the next one is going to be 2, 1, and 2, 3. And then the last one will consist of tuples that start with 3. So it will be 3, 1, and also 3, 2. So once you perform the actual unions, then you end up with a bigger set. And the bigger set just has 1, 2, 1, 3, 2, 1, 2, 3, 3, 1, and 3, 2. Is that making sense?
Yep.
So it is all spelled out. Okay, so this set here, the last one, is representing if I have three numbers in a box. Okay, on three cards. Okay, one card is labeled 1, and then the next one is 2, the next one is 3, and I want to choose 2 cards out of 3. These are the ways that I can choose those cards when ordering is important. And that's why you can see 1, 2, and 2, 1 are listed as 2 different elements because they are tuples. In a tuple, they are distinct. 1, 3, 3, 1 are here, 2, and then 2, 3, and 3, 2 are also considered distinct. So we have 6 possible outcomes when you are choosing 2 things out of when you have 2 trials and the first trial has 3 things to choose from. Is that okay? All right. Do we need more time on this slide, or we can move on? Let me double check to make sure the recorder is on. It is. So it recorded all the rain too, all the sound from the rain.
Yeah, this is gonna be really interesting.
So shall we move on to the notes? Okay, so this part is okay? All right. So in the notes, I'm just making one gigantic step here and say, if you consider the outcome that has I trials, okay, and you start with T as the possible outcome of the first trial, then it becomes a union, okay, we saw that earlier. You pick every single possible one out of T, and then you have E, which is the same as what we had before, but this time I use a recursive definition, okay, because I'm just saying that, oh, there are this many ways to choose the first outcome of the first trial, to choose outcomes of the first trial. Each one has to be Cartesian product with the possible outcomes of choosing everything except for E, and we have one fewer trials to consider as a sub-experiment. Is that making any sense? In other words, I'm looking at an experiment of I trials as one trial and a sub-experiment of I minus 1 trials. And that's why I can use this as a recursive definition. So when you do this computation, when this is all done, this particular set is going to look like what we had earlier, except it's going to be a lot bigger depending on what I is. And also depends on what T is. Is that okay? What do you think is the number of elements in omega I T? We have already dealt with this kind of computation earlier. Remember, we knew about the cardinality already. We just have not associated those cardinalities with I and T in this particular context. It will be the permutations of choosing I items from the cardinality of T.
Put in the calculator is backwards.
Huh?
The NPR, it's like 3 N 3 for N, and then R is 2.
Yeah, and choose R. NPR or P
3 choose
and R. All right. So are we still doing okay with this? This is not doing counting anymore. This is showing us every single way to choose I things out of cardinality of T many things. Is that okay? All right, cool. So the significance, which is the very last part of this module here, is counting is important because it is the denominator of discrete probabilities. In other words, I'll show you examples later on, but we need to figure out how many possible way things can turn out, and then we say, okay, but we're not interested in every single possible way, we're interested in specific ones, like the odds of winning the jackpot in lotto. So if you are focusing on both of those things, then you get a discrete probability. What are the chances of winning the jackpot in a lotto game, what is the chances of winning the second prize of a lotto game, and so on. So this gives you the denominator that you need to calculate probability. Is that okay? This entire discussion, not just omega, not just this kind of awkward omega definition that is recursive, but the entire module talks about that. So are we cool? Let's try to apply this, okay? So we'll apply this in the famous, birthday question, okay? So the famous question is, given a particular class size, I think we have about 35-ish students right now. So given 35 people in a room, what are the chances that everyone has a unique birthday? That's the question.
What do you define by unique?
Different.
How many students you said?
35.
Oh,
35.
Yeah, so we have 35 or n people in the room, okay?
yeah.
And we're not going to count the leap day as a possibility, so we just stick with 365.
Yeah.
So the question is, with 30 people in the room, what are the chances that there are no duplicate birthdays in the entire room? Yep.
By duplicate birthday, are you only looking at the month and day, or are you also considering the years?
Not considering years, just the date. So
how-
you're only considering the month and day of month.
Okay. So I'm trying to know how many people in here have the same like month and day, or all the people here who have different months and days.
The question is asking what is the probability
Right.
that we all have a different birth date.
Oh yeah, it's pretty high.
0.
Okay?
Pretty high.
So let's do some calculations. Let's see how we can figure that out. Okay?
It's like only 12, not like 30.
Okay, so the question is the probability of everyone in a room having unique birthdays. Okay, and we can use a concrete number. Concrete number is always good. And we'll say, this is n. Okay, n is the number of people. Okay. All right. So now that we have n defined as the number of people, and this is what we're interested in, there are two ways to think about this problem. The first way to think about this problem is to think about very simple cases first. What if this entire room only has one person? What are the chances that that person has a unique birthday?
0.
No, it's 1. It's 100%.
Oh, 100%.
Oh, I said big. I don't know if that would count. Like,
Okay, so the next one is, what if the room has 2 people? What are the chances that the 2 people in the room have different birthdays?
364 out of 365.
Okay, those are the ways to have different birthdays. You have to divide it by something to get the probability. Okay, so that's good. Okay, I like that line of reasoning. Okay, so let's think about that. So when n equals 2, which means we have 2 people in the class, we have 365 ways to choose a birthday for the first person, and then of the remaining days, we have 364 days to choose a birthday for the second person. Is that right? Okay, and ordering is important here. Okay, so whether I have the 4th of May 4th, or whether you have May 4th, is important because they are considered 2 different configurations. So that's why we are not dividing this by 2 factorial, because we are not looking at counting combinations, we are counting permutations. Okay? But then you have to divide it. This is the number of ways that we can have birthdays among 2 people so that they are distinct. But you have to divide it by the total number of possible ways to have birthdays between 2 different people, including on the same day. So if I don't care about uniqueness, okay, and I'm just asking, okay, how many ways can 2 people have birthdays? Well, What do you think that the answer should be? 365 for the first person, and guess what? 365 for the second person. Is that making any sense? So the ratio between these two numbers is the probability of two people in the same room having different birthdays. Is that okay? So that turns out to be a pretty easy number to figure out because we are only talking about the 365 cancels out with the 365, so we have 364, excuse me. Okay, 364 divided by 365, which is a pretty high chance, right? Kind of makes sense. So you can also look at it from the flip side, which means the chances of two people, at least two people having the same birthday when you don't have two people is 1 divided by 365, which is a pretty slim chance. Okay, what if n is 3? So when n is 3, okay, you just extend this reasoning. The first person has 365 days to choose from. The second person only has 364 days to choose from. And then the third person only has 363 days to choose from. Is that okay? So that gives you the total number of ways to arrange birthdays amongst 3 people where they are all unique. But when you look at the total number of arranging birthdays of 3 people, well, it's 365 days for the first person, 365 for the second person, and 365 for the last person, the third person. So when you compute this ratio, then it is pretty clear the 365 still cancels the 365. So we have 364 times 363 divided by 365 times 365. So if I were to just compare, how does this number compare to the previous number? Is it larger or less? Do we have a higher chance that people can have a different birthday, unique birthdays, or do we have a smaller chance that 3 people all have unique birthdays? Smaller. It is a smaller chance. So now the question is, what if n is 35? In general, what is, how we factor this n in? Okay, what do you think? What is the general equation? The general equation is to have the denominator being p, the number of permutations of, you have 365 as the possible outcomes for the first person, right? And then how many trials are we having?
35.
No. The number of people is the number of trials. That would be
35.
n, right? And then we divide it by what? What is the total number of possible ways to arrange birthdays, duplicate or not, amongst n people? 365 to the power of n. So that turns out to be the general equation of the probability, the chances of n people having distinct birthdays. And you can see how when n becomes 365, it becomes, it degenerates, right? When n becomes 365, the number of permutations of choosing 365 out of 365 is 365 factorial, and then you have to divide it by 365 to the power of n. Which one grows faster, by the way?
Compared to
The bottom one does grow faster. So that means this number will only get smaller and smaller. The ratio, the whole fraction, is going to get smaller and smaller. So now we plug this into a spreadsheet, okay? And we try to figure out for what kind of class size, what is the chances of not having duplicate birthdays. So let me pick out, I got a spreadsheet already, but I always like to redo it just to make sure that I did not do it wrong the first time. So let's do a little spreadsheet. And then we have the first column being n, and then the second column is chances that birthdays are unique. And then we'll have a third column too. The third column is really just 1 minus the second one, which is representing the chances that there are duplicate birthdays, which means at least 2 people share the same birthday. Okay. All right. So when n is 1, this number, we just plug in the general equation. So you can use permute, okay, as permutation. I think we have to start with equal sign. Permute. There we go. 365. Choose n. In this case, n is just whatever that cell is, and then this whole thing divided by 365 to the power of the same n, and we get something that is really, really close to n, and that's close to 1, and that's why it shows. Oh no, it is 1 because we only got one person, so that person has to have the unique birthday. Okay, that makes sense. So when you look at the chances of people having different birthdays, it's going to be 1 minus this number, which is 0. Yep.
So, like, the equation for, like, the thing, like, totally makes sense, but, like, intuitively I'm having, like, a bit of trouble understanding why exactly the numerator is a permutation and not a combination. Like, it makes sense, like, when you write it out, but
Right.
like, sort of by definition with the, like, order mattering and the order not mattering, that's kind of...
Okay. That has to do with the denominator itself is also counting duplicates. Because we are looking at the relative ratio between the two, so if the denominator is including duplicates, because 365 to the power of n means that the first person can choose any one of the 365 days, the second person can choose any one of the 365 days, so we are basically counting 1, 2, and 2, 1 as 2 different choices. So you have to do the same thing with the numerator so that it is calculating the right ratio between the two. All right, so at this point, it is easy. This is why I like spreadsheets, because you can do this. I did something wrong with the equation somewhere.
Wait, what did you do?
Okay, what did I forget? Hmm?
Just the
What did
first
you do?
column. You just force it to be
No,
midpoint.
Oh, that's right. Okay.
Needs to be incremental.
1 plus that. How about that? Then we can propagate this again. Okay.
Sheets are confusing. They're the devil.
There we go. Cool. That's why I like spreadsheets. You can fix one mistake quickly, and then we have all the probabilities there. Okay, so the probabilities have a lot of digits, which I do not like. So let's go ahead and fix that. So we go to Format. Where's my format?
It's on the tab.
Yeah, it doesn't do the right click, doesn't get to it. So we just want a certain number of digits. Yeah, that would do. I mean, unless you guys prefer your percentage, but that's close enough. Okay, so we can see that the chances actually decreases pretty quickly. By the time we get to 19, we are already talking about 62% versus 39%. So if we go down to 35, so when we get down to 35, the chances of at least 2 people in the class having the same birthday is actually significantly higher than the entire class having unique birthdays. It is pretty significant. I have one class that meets in rave hall because of the size of the class. It's about 60 people.
You just go. All right, cool.
So when you get down to 60, we are talking about 99% versus 1%. So in my CISP 310 class, assuming full attendance during the lecture, the chances of at least 2 people sharing the same birthday is 99%.
Oh my goodness.
There's only 1% of a chance that in the entire class, all 60 people have different birthdays. And the next one is already rounding down to 0. It's not exactly 0 because we're not quite to that point yet, but But you get the point. Isn't that interesting?
Like you could have like a bet at the beginning of class. Like, alright, who would like to bet that nobody here has the same birthday?
Yep.
Just to what is your formula for the third column?
The third column is really just 1 minus the second column.
Oh.
Yep. Because we are looking at the reverse, because the opposite of everyone in class has a unique birthday is at least 2 people have the same birthday. But the key word is at least, okay? So it is, so we don't know how it is distributed. Maybe these 2 people have the same birthday, those 2 people have the same birthday, or these 3 people have the same birthday. We don't care. We just say that at least 2 people have the same birthday. Yep.
How to calculate what are the odds if someone has the same birthday as I am?
Same year?
No, this is in birthday.
Okay.
Not including the year.
Not including the year, but just with you, right?
Yeah, just with one person.
Just with one person. So from that perspective, so you have a class size. The best way to think about it is, okay, what if you have 2 people? So when you only have 2 people, the chances of the other person having the same birthday as you is 1 over 365.
Yeah.
Okay. When you have 3 people, then it will be the chances of having 2 people have 1 person with the same birthday as you, and then you have to multiply the probability of the 3rd person also having that same birthday, which is also 1 divided by 365. So now it becomes 1 divided by 365 to the power of the number of other people having the same birthday as you.
Oh, so
It gets very small, and it keeps getting smaller and smaller exponentially.
oh.
And it has nothing to do with combination or permutation, because in this particular case, you are doing exactly the reverse. Instead of ruling out and saying without replacement, you're looking for a particular thing in the set. So that's why it is constantly 1 divided by the possible outcomes. You just have to multiply that x many times for x many people to have the same birthday as you. Question? Oh, okay, great.
So it's basically the negation of what we're doing right now.
I wouldn't say it's negation, it is just a different problem. Any other questions? No other questions? The rain has stopped, so now is a good chance to run to wherever you need to go. Yes?
Can you see the equation on the second column?
Yes. It's the permutation divided by the power. All right, I'm going to turn off the mic.
Like, мне тоже интересно, как он это, как можно,
Trying to use this with parentheses and everything. 265 choose 35 and then divided by 265 to the power. So I'm getting a different answer. I'm getting 0.18.
Yeah, that's exactly what we got. This is 60, right? You're talking about
This is
35?
35.
Yeah, we got 35 earlier.
Yeah.
Yeah, we have, it's rounded to 119, so
I guess so.
and that rounds up. Yeah, so we got the same number. Yep.
So I did the exercise which you had for the CNF, and like I came up with a whole different answer than what I checked. I went on what is it? Wolfram.
Wolfram.
Yeah, and